I want to review a little bit on solutions. I posted a video on beginning solutions that was quite a while ago. So basically, we have gaseous leaders and we have liquid leaders. Totally not the same thing. When we talk about solutions, we're talking about liters of either a gas or liters of a liquid or grams of a solid. So a solution takes in all that. Normally, when people think of solutions, they think of liquids, but that's very narrow scope of what a solution is. Solutions are, for example, the air in this room is a solution. It is a homogeneous mixture of chemicals. Homogeneous, meaning we can't distinguish one from another. For example, in this room, we've got nitrogen, oxygen, carbon dioxide, a little bit of carbon monoxide, hopefully not very much. So it makes up a solution because we cannot distinguish by looking at it the difference. So it's a homogeneous mixture. Oil and vinegar, a heterogeneous mixture. Hence, it's not a solution. It's got to be homogeneous. Vodka. Can you distinguish the ethanol from the water? No. So it's a solution. Gold ring. They add copper to gold to make it stronger because gold is very soft. Solution. You can't distinguish the copper from the gold. So all those are examples of solutions. And there's zillions of examples. Now we're going to be focused in on water solutions in here. And in your next chemistry class, same thing. They're going to focus, well, probably 99%. They'll focus on the water solutions only, other than a quick definition of what a solution is, which is what I just gave you. Okay, so there are two parts to solutions. Okay, so again, solutions are two or more chemicals in a homogeneous environment. Gas, liquids, or solids. Of those chemicals in that solution, there are two classes. One's called solvent, the other's solute. Solute is at least one or more, and solvent is the most, and there's only one of them. So, for example, in this room, let's look at the gases in this room. Most of the gas in this room is nitrogen. So nitrogen would be the solvent. Oxygen would be a solute. Carbon dioxide would be a solute. Carbon monoxide would be a solute. Vodka. Does anyone know the proof on vodka? Is it 80 proof? That means it's 40% ethanol, 60% water. So what's the solvent? What's the most? 40% ethanol, that's a drinking alcohol, 60% water. So which is the solvent? Water, right. So the ethanol is going to be solute. Coffee. I was just drinking some on the way here to get my spirits up. Been a long week. So mostly water, a little bit of caffeine, a little bit of stuff that makes coffee, all the oils. It's very complex. So the water is the solvent. Okay. And real quickly, normally I spend a lot of time on the qualitative aspect of a solution creation. where we take a crystal of something in water and show how it dissolves. However, all I want you to know is when you put a crystal of something in water, water is very polar. All right, whose poster is this? Nicely done. Very nicely done. Water is very polar. We've got the H's are partially positive, the oxygen is partially negative. So what happens when we, for example, we put a sodium chloride crystal in water, what happens is the water is pulls the crystal apart by attracting to the ions in the sodium chloride. Sodium is positive, chloride is negative. So the negative of the water is going to attract the positive of the sodium, pulls it out. Okay, same with sugar and water. What about sand and water? What happens if you put sand in water? Does it dissolve? No, it doesn't. And that's because the solvent is not strong enough to separate out the silicon dioxide, the sand. Glass is also silicon dioxide. So I have a glass of water. Why doesn't the water dissolve the glass? Because the water is not strong enough to pull the glass apart. So that's what you always have in duality in solutions. You have one force against another. Whatever one wins, okay, so the solvating force, if it wins, it dissolves. If the other force, called crystal lattice force, wins, it stays solid. Now, let's look at the quantitative aspect. When we talk about solutions, some solutions are very strong, very concentrated, and other ones are really weak. So we need a way of quantitizing that, and that's done via moles per liter. And when we say moles per liter, we're talking about solvent plus solute liters, which are wet, not gaseous. Okay, when you get into your next chemistry class, if you're going into the 1A route or the 3A route, you're going to be talking about two kinds of concentrations. One is molarity, and that's a capital M italicized, and I underline mine as well, or a lowercase italicized m. One's called molarity, the other's called molality. One is defined as moles per solute over liters of solution. Solution includes solvent plus solvent. Molality is moles of solute over kilograms of solvent. And they're slightly different. And molality is used a lot in things like, why does putting salt on your sidewalk melt the ice? That has to do with molality topics. And we're not going to be using molality here. We're only going to be using molarity. So moles per liter of total solution, solvent plus solutes. Okay, so what does a problem look like? Let's clear the deck here. So let's look at this. What's the molarity of the following solution? 34.5 grams of sodium chloride and 3.45 liters of water. Okay, first of all, we need moles of solute. What's the solute here? Sodium chloride or water? Water is the solvent. That's what you meant, right? Okay, so the solute then is the sodium chloride. So we need to figure out the moles of sodium chloride. We have grams of sodium chloride, so we need the conversion factor to go from grams to moles, which is the molar mass of sodium chloride, which is 58.44 grams per mole. Okay, so we need 34. And what is that? Okay, so we have 0.59 moles in 345 liters. Okay, by definition, molarity is per 1 liter, not per 3.45 liters. So you have to divide by 345. So that's 0.59 divided by 345. So you can do this in 1 step or 2 steps. I recommend, if you've never seen this before, do it in 2 steps. If you've done this before, you can do it in 1 step. Okay. Okay, how many grams of sodium chloride are there in 3.45 molar solution of sodium chloride? And you've got 5.67 liters. Okay, so we need grams on this here. Okay, so okay, so how can we get moles if we know the concentration? Well, we need to have the liters cancel. So we've got liters right here. Liters cancel, leaves us with moles. If we have moles, we can go to grams. So we've got 345 times. I want to take the 19.8 moles and get grams. So that's 58.44 grams over 1 mole. Moles cancel. Okay, so that means we have 1160 grams of sodium chloride in that solution. Now, there are two ways to calculate concentration. One is with dry ingredients, like these two problems are. The other was to take a concentrated solution and dilute it. Two different ways to calculate concentration, depending on what you start with. If you start with a dry ingredient, or you're trying to calculate a dry ingredient that was put in there, that's these two problems here. Let me show you. Are there any questions about these two guys? Both of them, think of them, both of them are two-step problems. You can do them all in one, but think of them as two-step problems cognitively. Mathematically, you can do it all in one step if you want. Okay. Okay, if we have if we have 2-liter solution and we have 4 molecules of something, let's say 4 molecules of sugar, and we add 3 liters to that. So we end up with how many molecules of sugar do we have after we throw in 3 extra liters of water? 4, right? We haven't put any extra sugar on. Sugar stayed the same. The only thing that changed is the water. So now we have 4 sugars. This is considered a concentrated solution, and the other one is considered the dilute solution. Also, think about this as being the initial and the final. So what's the only difference between these two? Water, exactly. So that means four sugars, 2 liters, 5 liters. The reason why this is considered concentrated is because we have less solvent in this one. Same amount of moles or molecules or moles, more solvent. More solvent, same number of moles means it's more dilute. So the initial moles of sugar equals the final moles of sugar, or the concentrated sugar equals diluted sugar. Moles. So if we looked at moles per liter concentration, so let's say those are 4 moles. We have 4 moles over 2 liters. Over 5 liters. Initial or concentrated, final or dilute. Okay, moles stay the same. So if we ever have a concentration, we can find the number of moles by multiplying by the volume, because that cancels out liters. So okay, this is a very important relationship. We're going to be using this in lab today. Concentration times volume equals moles. Today we're going to be doing something called a neutralization reaction. And by the way, the lab today, I want you to do data only, because I need to finish up the lecture tomorrow on some of the calculations you have to do in the lab. So Friday, folks, just unless you've had this before in high school or something like that, hold off on doing the calculations. I know you're upset about that, but okay, so let's talk now about a problem, a dilution problem. Okay, so we want to end up with 4.57 liters of a 2.34 molar solution of sodium chloride. We don't have dry ingredients available, but we've got this super concentrated sodium chloride solution. So what do we do to take an X amount of the concentrated stuff and dilute it down with water until we get 4.57 liters of the 2.34 molar? Now, concentration times volume equals moles. We've already talked about the moles don't differ from the concentrated versus the dilute. The moles are the same. That means we can set equal concentration times volume equals concentration times volume. So we've got concentration and volume right here. So this is the dilute. Okay. So what we're talking about here is now moles sodium chloride equals moles sodium chloride. So the moles haven't changed. Solvent volume has changed. Okay, is everyone okay how I got this up here? Concentration times volume equals concentration times volume. We don't know the concentration of the concentrated stuff yet. We're going to calculate it. Okay, so we're going to solve for liters. It's a standard equation. So we've got all I did is I divided both sides by 12.45. I divide both sides by 1245. The 1245 cancels on the right and on the left. So I multiply 2.34 times 457, hit the divide key, 1245. That gives us 0.859 liters of the concentrated stuff. Now the question is how to make it. And that's step one, is you have to calculate the volume of the concentrate required first. Now our total volume is 457. We're going to end up with that, right? That's the total volume. Part of that new volume is going to be the concentrate. The rest is water. So I'm going to subtract 457, 8. So how do you make it? You take 0.859 liters of the concentrate and add to that 3.71 liters of water. That's how to make it. Let's two-step again. Okay, first, you calculate liters of the concentrate. Then you figure out how much water you got to add to bring up your final volume in the dilute. So this is a dilution problem. Okay, does everyone see where I got the numbers on this? Okay. Let's do another one. Okay, so we start with 2.33 liters of a 678 molar sodium chloride solution. Now we dump in 312 liters of water. What's our final concentration? Okay, so this is a dilution problem, kind of the backwards of the one we just did. Okay, so let's define the concentration. Instead of M, let's call it moles per liter. So we've got oops. Okay, so now we're going to add in okay, so we're starting with 6.78 moles per liter, and we have 233 liters of it. We dump in 312 liters of water. What's our new concentration? Well, how do we do this? Think about definition of concentration, moles per liter. What's changed, moles or liter? Liters, yeah. We didn't do anything with the salt. Salt stayed the same, so moles stayed the same. So now we're going to have so now we have 678 moles, and we have 545 liters now. Everyone see where I got the 545? We started with 233, added 312, come up with 545 liters. So what's the concentration? Concentration is moles per 1 liter. So we need to divide the 678 . So when we dilute something, does the concentration go up or down? Down. So our answer should be less than what we started with. Okay, we started with 678, we ended with 124. So that number makes sense. Yeah.
Like at the very beginning, 6.78. Can that be like 6.78 by 2.33? Because
Yes, exactly. So what he's talking about is, do I truly know the number of moles? Not yet. This just says how many moles are in 233 liters, not how many moles there are, okay? So what we're going to do is we're going to modify this to reflect, first we need to calculate moles of sodium chloride in there. How many liters are we starting with? Now that'll give us moles of sodium chloride. And we need to start with moles, not concentration. Okay, so in that solution, we have a total number of moles as 15.8 moles. Okay, no liters yet. And what's our total number of liters? 545. We have 289 moles per liter. And we started with 678. So again, moles are your friend. Always think in terms of moles. Now, your next chemistry class, I want you to go into that chemistry class thinking moles, 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 moles. Most of what we're covering in this class that are weaknesses on incoming 1A and 3A and 2A students is a concept of the mole. In stoichiometry, what we did for Unit 4 and what we're doing with solutions. Mole, mole, mole. Now, tomorrow I'm going to talk about acids and bases and neutralization reactions. Because when an acid and a base get together, something is neutralized. That's what our lab is about. Okay. Who in here is planning to go into 1A? Okay, quite a few of you. Okay, again, this is really important, this concept of the mole. The other big deal is naming. Two big areas. So test 1 or Unit 1, Unit 4, Unit 5, and naming are crucial units. So keep your notes. You can always get to the videos via YouTube if you can't get into Canvas, plus all the others. Who in here? Last last night I put a concept map together for a new project I'm starting. Who in here uses Chat GPT? Does anyone? Okay. Okay. What I'm trying to eliminate is the requirement to buy a textbook using artificial intelligence. Because with Chat GPT, you can actually query the data in the artificial intelligence database for things like chemistry stuff. You can query it for example problems. You can query it for homework problems. In my syllabus, I have something called student learning objectives. That's the start of your prompt. You go through and use the student learning objective prompt into your AI, they'll give you background on it. And if you ask it for practice problems, it'll give you practice problems. Practice problems with answers. It'll give you practice problems plus answers. It's really quite cool. And it's free. Yeah. Good. I'm glad. Thank you for sharing that with me. I was subbing over in Sac City for a colleague of mine, in their 1B class. And she was out. She was totally out for most of the semester. And the students were sort of like on their own. And a lot of the students survived that class with no lecture from their instructor. I mean, zero. They had 2 weeks in the beginning. That was it, using AI. And I was going like, how powerful is this? You can get it. Did you pay for yours? How much did it cost you? Was it like $50? Yeah. Now, whenever you use any of these, yeah. Yeah. And a lot of teachers are clueless about AI. When during COVID, um, one day they sent me an email saying, all your stuff is online now. Have a nice day. We had like 6 teachers retire that quarter, that semester. 6. They were elderly and they didn't like technology at all. They were strictly overhead projector of years worth of slides. That's how they taught. The tests, they collected them back. So you never had an old test to look over, a practice test, none of that. Those are the ones that all retired. They didn't embrace technology. What this does, this puts the student in control. The concept is called metacognition, where the student is in control of their own learning. It's very powerful. And then teachers need to use it as a leverage. And so anyway, I'm starting to work with some people over at Sac City about putting that together. And this is how I got involved with video. Is I was on a cohort up in Washington about how to increase the media in lectures. I said, well, let's just do a video. So anyway, that's why I started doing videos. Embrace the technology because your students will or have embraced it already. So join the club. All right, that's what I wanted to cover today. And come on up and grab your tests. And